Let's practice regularization. We will be using housing regularize RSME Python notebook here and the housing aims CSV file. The CSV file contains the price of the household and 75 other attributes like lot area and year built, etc. that can be used to define the price of the house. We will use all of these attributes to predict the house prices. In the notebook, we first import pandas, numpy, the graph library, and sklearn, and all the prediction libraries that we will be using are right here. Here we are simply reading the CSV file into our DF, and when we print the shape, we are basically getting the number of rows, which are 583, and the number of columns, 76. But here we can't see all the columns. So using this command, we can we can see all the columns. If we do df.head again, now we can see all the columns right here. Next, we will create dummy variables and we will remove the first category by using the drop first equal to true. And now if we print the shape again, we see there are 209 columns now. Moving forward, the next question is to report the skewness of the price attribute. So we can simply select the attribute and call the skew command on it. And this is the skew value for the price attribute. And using the hist command, we can plot the histogram for the price attribute, as we can see in the graph. Similarly, we can use the log command and convert the the price attribute and add it to our existing data for their log values. Similarly, we will print the skew value for the log price attribute. And this is the skew value for the log price. And this is the graph, the histogram for the log price. Moving forward to the next question, we'll run a regularization model using the five-fold cross validation without standardization and report the root mean square error value. Okay, so the y is our log price, which we calculated just before this, and x are all other variables. So in this first line, we are simply deleting the price column because we are going to use the log price column. So our y is defined as the log price column, and x would be all the other values other than the log price. Here we are creating a linear regression model and using M1 for it. Then we are simply calculating the mean squared error given the model, the x and y values. And when we print this value, you see we have 5 values here. What this means is for 5-fold cross validation, so say we have 500 values, 400 are used for training and the remaining 100 are used for testing. So similarly, we have about 500 values here. So we have the first value here where random 400 rows must have been used for training and then remaining 100 for testing. Here again, random 400 values used for training and 100 for testing. Similarly for the other 3. Here in this line, we are simply taking the mean from all of the 5 values and doing a square root on that to get our root mean square error, which is this value. Next, we will standardize the predictors, basically the attributes, run rigid regression, and plot the estimated coefficients as a function of the parameter. So here we are simply using this command from sklearn and standardizing all the attributes which we already defined in X, and we are storing them in x1. Also, we are defining this a, which is basically values from 1 till 200 in increments of 10. So basically 1, 11, 21 up until 191. The last 200 is not included. Here we are defining a ridge model in M2, and we are going to add the coefficients for each of the attribute. Here we define the ridge model in M2, and let's quickly just look at what the ridge model is. It is the linear least squares with L2 regularization, and we have an alpha here, which is like the regularization strength, and for all the values in A, which is the array which we defined in the previous value, we will be using all of these values as alphas, and then we will use the fit command. Again, looking quickly at the meaning of fit, it basically means to fit the ridge regression model which we just defined right here. And we will be storing all of the values, all of the estimate, all of the fitted estimator values which we get from the fit function into this coefficient array. And then we will be plotting all of these alpha values to their corresponding coefficients, the fitted estimator values that we just calculated. And once we plotted, this is the plot we get. Moving forward, we will run the ridge regression again, but this time using the 5-fold cross-validation method, which we just discussed above, and report the root mean squared error. Here, we are using the ridge cross-validation method, where we are going to use the alphas as defined in the previous question, and the cross-validation, we will be using 5, similar to what we did before. And we'll call the fit function here, passing in the attributes and the y value here, which was our log price. And we'll calculate the mean squared error, passing the model, the attributes, and the predicting value. Similarly to the standard regression, the MSE mean squared error for cross validation, we have 5 values. So we will calculate the mean from all these 5 values, and we'll do a square root on that to get our root mean squared error, which is this value right here. Next, we will be running lasso regression. Similar to the A, we are now defining an A1, which will have values starting from 0.001 up to 0.3 in increments of 0.001. So this will have a lot of values. Here we are defining a lasso model, and the maximum iteration would be 10 to the power of 5. So for all of the values here in A1, we are going to calculate the coefficients using the lasso model right here. So we will set the alpha here, and the alpha would be the values from the A1 array, and we will call the fit method, passing our attributes and our log price value, and this will give us a value which will be appending in the coefficient array. And using this graph library, we will plot the alpha values and the coefficient to get the graph between the lasso coefficients and the alpha values right here. I'll be creating a lasso regression using the 5-fold cross validation. Here we are creating the lasso cross validation model, and then we are calling the fit command on all the attributes and our the prediction value, which is the log price. And then we are calculating the mean squared error using the model selection cross validation score command, passing in the model that we created, the all the attributes, and the predicting value, which is the y, our login price. Again, since we are using 5 cross validation, if we print the mean square error, we will get 5 values. So we'll take the mean of the 5 values, and do a square root on that to get our root mean squared error. Next, let's calculate the count of number of non-zero coefficient for lasso regression. So as we created the model in the 7th question, if you print the length of the coefficients in that model, we'll see we have 208 coefficients, and we can use this command to print all the coefficients. These are all the 208 right till here, 208 coefficients. Next, there is a command through which we can get the non-zero coefficients as well. If we print the length and the value here, we see the length is 1 because it's giving us the array of all the non-zero coefficients indexes right here. And the easy way to access is to get the first element right here using this subscript. Here, if you see, we have 58 non-zero coefficients, and these are the indexes of those non-zero coefficients. Next, we'll compare the root mean squared errors going from the bringing or the first regression model to the recent one, the lasso regression. So the lasso minus the first one, linear regression, we can see there is almost 40% down, 40% change in root mean squared error value from 0.289 to 0.176, which is good. The less the RMSE, the better the model.